In this video, I'll describe how to use the chi-square distribution for research questions related to independence. Over the past decade, researchers have investigated the relationship between diet and cancer. Researchers wondered whether eating fish reduces the chance of getting prostate cancer. They surveyed 6,272 men and asked them how much fish they typically ate. Then they followed the men for the rest of their lives and identified whether or not they got cancer and counted the results. Then they found the totals for each row and column. So in this scenario, there is one population with two categorical variables. Now, the null hypothesis is that there is no relationship between the amount of fish you eat and whether or not you get cancer. In order for us to more clearly articulate this, we need to specify what all of the parameters are. I'd like you to pause the video and think about what these parameters are. It turns out there will be 8 parameters, but there are 2 completely different ways to specify them, and each corresponds to a slightly different version of the null hypothesis. For the first way, one parameter is the percent of people without cancer who never ate fish, which we can represent as pi sub nc comma never. And another parameter is the percent of people with cancer who never ate fish, which we'll write as pi sub c comma never. And I've highlighted the statistics that would correspond to these parameters just to illustrate how they're related to the data in the table. Now, if the null hypothesis is true, and your diet has no impact on whether or not you get cancer, then these 2 percentages should be equal to each other, and they should both be equal to the overall proportion of people who never eat fish. And there would be 3 additional equations like this. But before we write those, let's look at a second way to specify the parameters and null hypothesis. There is the percent of people who never eat fish that got cancer, which we can write as pi sub never comma c. Like before, I'm highlighting the statistics that correspond to these parameters just to illustrate how the parameters are related to the data in the table. And then the percent of people who eat fish as a small part of their diet that got cancer, which we'll write as pi sub small comma c. And the percent of people who eat fish as a moderate part of their diet and got cancer, or pi sub moderate comma c. And the percent of people who eat fish as a large part of their diet that got cancer. And if the null hypothesis is true and the diet has no effect on cancer, then these should all be equal to each other, and they should all equal the overall percentage of people who got cancer. And in this version of the null hypothesis, there would be another equation with the other 4 parameters, but I'm putting this here just to contrast with the first set of parameters in null hypothesis. They look pretty similar, and they'll both produce a valid null hypothesis, but they're using slightly different versions of the parameters. For now, I'll continue on with the second set of parameters and null hypothesis. So the rest of the parameters would be the percent of people who never ate fish that didn't get cancer, and the corresponding percentages for the small, moderate, and large amounts of fish. If the null hypothesis is true and eating fish has no impact on whether you get cancer, then these percentages should all be equal to each other, and they should all equal the overall percentage of people who didn't get cancer, which is 5,806 out of 6,272. After creating the null hypothesis, we use it to compute the expected values, the number of people in each cell of the table, assuming the null hypothesis is true. I'll make some space to compute these values. Now, for the number of people who never eat fish, there are 124 of them, and if the null hypothesis is true, we'd expect 5,806 out of the 6,272 of them to not have cancer. So we'd expect 114.79 of them to not get cancer. Similarly, there are 124 non-fish eaters, and would expect 466 out of 6,272 of them to get cancer, which is 9.21 people. And we'd keep on multiplying the proportion for the column by the number of people in the row. So now we have our observed values and expected values, and we need to compute a statistic that lets us summarize the difference between the observed and expected values using a single number. We do this using the chi-square statistic. So first we'd take the observed value and subtract the corresponding expected value, square the difference, and divide by the expected value. Then it would repeat this process for the next pair of observed and expected values, and add. Then it would repeat this for the next pair of observed and expected values, and continue this process. And after doing all of this, we'd get 3.68. This number summarizes the difference between the observed and expected values. Finally, we need to determine whether the statistic is strong evidence against the null hypothesis. Each of the expected values is at least 5, so we can look at the chi-square distribution. But first, we need to know which chi-square distribution. That is, we need to compute the degrees of freedom. In our observed values, the totals for each row and column are fixed. For example, there are 5,806 total people who don't get cancer, and there are 549 people for whom fish is a large part of their diet. So, the value in this cell can vary, as can the value in this cell and this cell. But since the total in the column has to add to 5,806, the value in this cell would be fixed. Since the first row has to add to 124, the value of this cell is fixed, as is the case for these other 3 cells. So overall, there are 3 cells whose values can vary, so there are 3 degrees of freedom. So we can look at a chi-square distribution with 3 degrees of freedom that is created from a null model. Then we'd look at the chi-square statistic and compute the probability of getting the statistic. In this case, this probability, the p-value, is 29.8%. What this means is that if the amount of fish you eat has no impact on whether you get cancer, and we took many samples of 6,272 people, we would get a chi-square statistic of 3.68 or larger in 29.8% of these samples. So this is not evidence against our null hypothesis that the amount of fish you eat doesn't affect whether you get cancer. Let's summarize what we've done here. So in this video, we did a type of analysis called chi-square for independence. It is used for research questions that ask whether 2 categorical variables are independent from each other. Although the type of research question is different, the method of analysis works just like it did for chi-square for homogeneity. And now we've seen 3 types of scenarios that can be analyzed using a chi-square distribution. Chi-square is used when working with categorical variables. There was goodness of fit, where we had 1 population and 1 variable, homogeneity, where we had multiple populations and we compared their distributions of 1 variable, and in independence, we had 1 population and we checked for association between 2 variables. In all of these versions, we compared observed counts to expected counts, where these expected counts were based on our null hypothesis, and we did this comparison using the chi-square statistic, which measures the difference between the observed and expected counts using a single number.